Okay, today's lesson comes from section 5.3. We will be learning to factor a quadratic expression. So, you probably remember a little factoring from Algebra 1. Probably could have spent a lot more time on it, is what we found. But let's review those different factoring methods first before we decide what you do and don't remember from factoring. So, some people will like to say it was done at the end of the year, so it was a hard part of their process. But let's do something here quick before we even start on this page. So let's clear this background for a second and say, remember factoring. Factoring with numbers. If I just gave you a regular number, 24, and if I start saying, what are the factors of 24? People start listing, oh, one is, but you usually should be listing them as groups, the two factors, the two things that multiply to give you 24. So then we'd go 1 and 24. We'd go 2 and 12, 3 and 8. You don't have to go in any order. You can go 6 and 4. Right? And you go through your list and you say, is there anything else? Now, here was a quick trick. When you did factors of numbers, you usually listed them in a set previously instead of just listing, because some of the numbers got awfully big and you couldn't remember if you got them. And the rule was, if the factors meet, then you know, or if you've checked all the factors until they meet, then you know whether your list is complete. So an example here would be, if we did do them in order, we'd go 1 and 24, and we say, okay, yeah, 2 and 12, and so then 3 would get paired with 8, and then 4 would get paired with 6, and the only number we would have to check now is a 5. If we went in order, went right on down, that would tell us there's nothing between 8 and 12, nothing between 6 and 8, nothing between 12 and 24, and we had all the factors. And the bigger the numbers get, if we start getting into triple digits and big double digits, it's harder for our head. We're not using a calculator to do it, but that's a quick way to tell. Now, we're going to be doing the same thing, but we have quadratic expressions. We don't have just single numbers. So there has to still be two things on a simple trinomial. Here's one of your basic trinomials. On a simple trinomial, we're looking for these two things that multiply out, and they would probably be binomials in most cases, that would multiply out to give you your trinomial. These combinations would be the factors of your trinomial. So that's where we're headed. Now there are several different ways, to get there. So let's go through the different types of factoring. One of them, the first one, and the most basic, is called the GCF. So when you think greatest common factor, I hope, when you think GCF. Greatest common factor is, what do these things share? What do they all have in common? And I have two different examples of that. So let's look at number 1 here first. 27c squared minus 18c. If you looked at that, you should be looking at it both as numbers and as variables. What does everything have in common? So if you break it down into those two parts, the numbers, 27 and 18, what is the greatest common factor that they have? Most people would say 9. If you were thinking 3, you're on the right track, but it's small. It's not the greatest. So you want to always go for the biggest number they have in common. So start with, does 18 go into 27? The answer is no. So then what's the biggest number that goes into 18 that also goes into 27? And start that way. Then you look at your variables, c squared and c. What's the largest amount of c's they have in common? And in this case, they each have a c. So we have 9c as the greatest common factor. So if 9c is going to come out as the greatest common factor, think of it like division. The opposite of distributing, we're going to go distributing backwards and say, okay, if I have 9c times what is going to give me that first term of 27c squared? Some people also like to think of it this way. 9c goes into 27c squared how many times, and what's left? So either way, you should get the term we need here. So 9c times 3c should be your first term in our parentheses. And then subtract. 9c goes into 18c 2 times. And if you would now in your mind to check it, and that's what this is, to check it, you should be able to take 9c times 3c and get 27c squared, 9c times your 2 and get 18c, and it better match what you started with or you know you have a problem. Now, that's your answer, that's your check. This piece that you started with are the factors. So what are your factors here? 9c times 3c minus 2. Those are the two things that multiply to give us 27c squared minus 18c. Again, that's called greatest common factor. All right, from there, we have a different looking one. We basically have some parentheses, we have quantities, but notice both quantities, both parentheses are identical. So instead of multiplying this all the way out, which is what first inclination is, to get rid of the parentheses, no. Look at it again as, what does this first group have in common with this second group? And right now, the only thing they have in common is that parenthesis 2z plus 1. So again, we're going to pull out that common factor. 2z plus 1 comes out as the GCF. Then times by what remains. If 2z plus 1 comes out as a factor, there's only a 5z left in that first part. And again, if 2z plus 1 comes out of that second part, you have a subtract 2 that's left. And again, if you multiply this out, or at least check to distribute, these should be the factors, and your check step would be more like, well, that's going to be 5z when you multiply 5z times 2z plus 1. That's your first combination, and that would be a negative 2 times 2z plus 1, and those are your factors. Now, the question is, why wasn't this original statement in black already considered your factors? Because in factoring, it's two things that multiply to give you your answer. Here are the two things, one parenthesis, then the other. Up here, you have a subtraction sign between the two. That does not signify multiplication. You do not have two things that are multiplied to give you that answer. So our factors in this case would be 2z plus 1 times 5z minus 2. And again, this would be the first method of factoring called GCF. On to the second. The second type, and I have to say we are having fun now, right? Because that's what factoring is. So we're going to use this fun factoring method to now factor a new possibility. In this case, we have a trinomial, x squared plus bx plus c. In this trinomial, you should notice that the a term is a 1. Right? So if you know a equals 1 in your statement, you will be able to use this method. And I like to call it the chart method because you're making a little multiplication slash addition chart as you do this. So where does it come from? I know it's going to break down into two things that multiply. And I know because of the FOIL process, first times first has to be my first term, which is that x squared. So I know that has to be x. And I know last times last has to give me the 27. So last times last could give me 27, but there's lots of things that multiply to give me 27. Those same combinations, though, if you think about the FOIL, if you go through, and we know we're going to put some numbers here, and we know The last term times the last term has to give me 27, is what we just said. But then there's that FOIL process. First times first would give me x squared. Outside times outside would give me so many x's. I'll just call it. And then inside times inside gives me so many x's. Oops, so many x's. And then last times last has to give me this last term. The next piece is that these two things here in the middle get added up because they're like terms. They're both x's. So the rule goes, what multiplies to give me the last term, which in this case is the 27, has to also add to give me that middle term. And our middle term here is a positive 12x. So if we follow that procedure now when we do our math, we will be able to come up with numbers that work. So ready? If you make this little chart on the side of your paper or in your head as you get going, if you're good with your times tables, you're thinking, multiplies give me 27, adds to give me 12. And you can sit there and start adding and go, oh, let's see, 1 and 11, you know. But the question is, are you going to get there faster by multiplying or are you going to get there faster by addition? And the answer there goes, how many different numbers multiply to give you 27 versus how many different numbers add to give you 12. If we're talking positive and negatives, and if we stick to integers, I think you're going to have fewer that multiply. We're going to be here all day adding to get to 12 if we include negative numbers. So think of using your multiplication statement first. If you can find something that works there and then check it down in the addition problem, I think you're going to be able to get to your result, get to your answer, and move on to the next problem so much quicker. So here we go. What multiplies to give me 27? Well, we did that. 1 and 27. 3 and 9. Well, wait a minute. As soon as I say that, 3 and 9 also add to give me 12. So if I put the 3 and the 9 here, and they make that work to 27, and the 3 and 9 also work to be the 12, I should be able immediately to go to my statement, put those numbers and their signs, so plus 3, plus 9, in. And again, those should be my factors, but let's just check. First times first, x squared. Outside's 9x. Inside, 3x. Last times last, total of 27. Collect like terms, x squared plus 12x plus 27. We're back to what we started with. That's exactly what we wanted. So our factors here are x plus 3, x plus 9. Now somebody's question usually is, well, can't I just put negatives and stuff like that in? It will not come out to be the exact same combination. It will change the middle term, it'll change the last term, it'll change something. So you need to make sure x squared plus 12x plus 27, the only factored possible way is x plus 3 times x plus 9. All right, so let's go a little quicker through this one. If we now know that rule is what multiplies to give me the last term will also add to give me the middle term. So that's what we're talking about as the little chart you want to memorize each time you do it. And I don't write that down. I just write the little combination. And some of you can do that, you know, in your head. What multiplies to give me, in this case, we got a negative 54 that adds to give me the middle term, which is also negative. So if we start looking at that, what multiplies to give me? Multiplies to give me a negative means I got to have a positive and a negative. So start thinking of those combinations. One of each. Couldn't have two negatives, right? But we got to be able to add to get to 15. So right away people say, well, let's see, 9 times 6 is 54, yeah. But 9 and 6, okay, if I put a negative on one of them, then that's not going to give me a 15. You know, they would if we just added. So 9 and 6 have to be out. What about like, and don't forget, 2. 2 and 27 in this case. 54 is even. So 2 and 27, oh, those look to be a little too far apart because we need to add to get a 15. All right? So you keep going. Maybe like a 3 and a 18. Well, 3 times 18, okay, one of them could be negative, and I think we found it. So right there, we would be writing our combination of, we know it has to be x and x because of the x squared, and now we can say we need more negatives in the addition, so we can say a negative 18 with a positive 3. Done, end of problem, there's our factors. So that's called factoring a trinomial using the chart method because your a term is 1. There is no number other than 1 in front of that x squared term. So you're using your multiplication and addition facts to help answer those quickly. All right, let's move on to step 3. This will look a lot like what you just saw, with the difference being, again, we're still having our fun on factoring now, but this time we have an a value. So look at it carefully. That a value will not be a 1. And if we don't have an a value of 1 and we have something else up front, that means we have a slightly different process. So in our example here, our a value is a 5. We have a middle term and we have a last term. So in relationship to what we were just doing, yeah, we're on the same track. We're going to have two binomials that will multiply FOIL to give us 5x squared plus 14x plus 8. But because we have an a term that's not 1, we have to do something different. And here's the work. List the factors of that a term. So we know 1 and 5. Now sometimes you'll have more. Don't switch around and say, well, 5 and 1. Nope. That's the same combination. So if it would have been maybe a 12, we would have had a 1 and a 12, a 2 and a 6, a 3 and a 4. Lots of choices. Here we just have the 1 and the 5. Also list the factors of the last term. 1 and 8, 2 and 4. And again, you really don't have to worry about signs right here. You'll work out the signs as you write and put your numbers in. So again, using that idea, first times first has to give me the first term. Last times last has to give me that last term. And then we know outside times outside and inside times inside must add to give me the middle term. So we got a little smiley look there, and we're going to have to combine it and make sure that it truly does smile, although we don't have a right answer. Now, the next part on this one is we only have that one choice, 1 and 5. So we know 1 and 5, x and x, because of the x squared, are our only choice up front. Now, I could have put it in as 5x in the first and 1x in the second, and that will not make a difference in your work. Now, the next, I like to call this method trial and error, because unless you're just really good with your multiplication tables, addition and subtraction, you will have some trials and you will err, and you will go and try something else. And so you will have some success and you will have some failures. So at this point, I would go and choose the 2 and the 4. Reason? With experience, you find out that there are more choices when you work with the factors that are closer together. So I would put the 2 and the 4 up here first, and when we put the 2 and the 4 in as we're saying them, and we check, 2 times 5 is 10x, 1x times 4 is 4x, and you add those together and you get 14x. There's your smiley guy in the middle. So now all we have to do is put our signs back in. And again, you could check it, but we just sort of did. First times first is 5x squared. Outside is 4x. Inside is 10x. 10x and 4x add up to 14x. Last times last gives you the 8. So you do get a perfect trinomial when you finish. So this is called trial and error. It's a little different because you have that a term that is no longer 1. Next method. Next method is going to be a little different because look how it starts. It is not a trinomial, and the title tells you that. It says we're the difference of squares. So if we're the difference of squares, we have some unique characteristics. A square and a difference has only 2 terms. So right away, if you see you have 2 terms, you definitely do not want to try one of your trinomial processes. You definitely want to jump in and say, oh yeah, it's got to be this one. All right, now, difference of squares can be done numerous times in a problem. But all it is off to the side here, if we did an x squared minus 4 combination, which both of those are perfect squares, and both your terms have to be perfect squares by the name to do this. And if there's only two terms, you got to think. It's like our trinomial, and they're both perfect squares, so we know what the values have to be because, you'll notice, there is no middle term. There is no x term. So that means it is canceled out some way, gone away. And the only way it could be if one's plus and one's minus, or one's minus and one's plus. And so the middle terms will cancel out, but everything else will be fine. Factor it or FOIL it. First times first is x squared. Outsides is positive 2x. Insides is negative 2x. Last times last gives us that negative 4. These guys will cancel, so all we have left is x squared subtract 4. That's the thinking. So look up here as we start this one. Check, and the rules are, is the first term a perfect square? Yes. Is the last term a perfect square? Yes. Is that a subtraction sign? Yes. Then you should be able to immediately write it in your two combinations of what will remain. So what is that perfect square for 16x to the 4th? And you should be saying 4x squared. What is that perfect square that'll give you 81? 9. And there only can be one number, and then we know we need one plus and one minus. Now, that will FOIL out, and that will give us 16x to the 4th minus 81. However, you need to double check. You have two terms remaining again. In this first parenthesis, perfect square, subtraction sign? No. But in the second parenthesis, yes, it still works that way. So that means you could even go further. So in the second parenthesis only, if I'm still a perfect square subtraction sign, take me down one more level. So that means, what is that perfect square for 4x squared? Well, most people would say 2x. What's that perfect square of 9? Well, 3. And then again, we need one plus quantity and one minus quantity. And you bring that first parenthesis that could not be broken down back along with your broken down ones, and that will be your combination. So this one actually ends up being 3 factors that multiply to give you 16x to the 4th minus 81. This is called factoring completely. If you don't do this last step, so to speak, then you would have factored, but it just wouldn't have been completely. So, difference of squares. Last one is called, the last combination we're going to talk about today, is called factoring using perfect square trinomials. Now, perfect square trinomials, they are what they say, but you got to look. Because once we've introduced all of these methods, I will tell you, GCF always should be looked at as the first thing to do. Because greatest common factor, if there's an extra term in there, you always want to pull it out. You always want to reduce the trinomial as much as possible before you begin. So in looking at this one, you can see that everything's even. So they do not have an x term in common, but they do have that number of 2. So if we pull that number of 2 out, watch, and it's sort of magical, we will have an x squared minus a 12x plus 36. Now if you look at that, perfect square trinomial. This is our trinomial. First term is 1. You could solve it that way. But better yet, ask yourself, is the first term a perfect square? Yes. Is the last term a perfect square? Yes. And I'll say go back and say that was an x and this was a 6. And if you multiply those two together, 6x, and double it, we're undoing that process we did earlier in the chapter. Doubling it would give us the 12. That would give us exactly what we need. So we now know that that is a perfect square trinomial, and we can just write one quantity that's squared that will give us our x minus 6 combination. The 2, the GCF, would be brought straight down that we pulled out. But if you FOIL just the x minus 6 quantity squared part, you would get that shortcut rule, x squared Minus 6x doubled is 12x. Last times last gives me a positive 36, and we would get back to what we started with. So our factors here are 2 times the quantity of x minus 6, that quantity squared. If you don't like writing it that way, yes, of course, this breaking that quantity and expanding it into 2 would be the same, but it takes more time. You recognize it. I'm a perfect square trinomial. Perfect squares are written as perfect squares. That's the short version. All right, so those are the 5 different types of factoring. The last thing they ask is, well, if you can factor, then you should also be able to solve. So the zero product property rule says, if you have 2 things that multiply out, and they call them P and Q, and I'll just say if we have 2 things that multiply out to equal 0, they're saying P, the first one, could be equal to 0. And if that's 0, then we don't care what that is, the second parenthesis. Or the second one could be 0, then we don't care what the first one is. And last but not least, they both could be 0, because we'd have 0 times 0 equals 0. So, if we start off with a trinomial, a binomial that can be factored, and we break it down into its factored form, then you should be able to say what the zeros of that product could be. So let's try 1 or 2. Start this first one. Now the only difference is we're starting off with a p of x, a function notation. That's okay, because it says a 0 of a function is any number such that the function would come out to equal 0. All right. So let's work it through first, and let's just factor the function. Now I only have 2 terms here. I'm looking first, GCF, see if they have anything in common. I see an x. So let's pull that x out, leave everything else inside. We would get a 5x plus 9. And again, distributing in your head, 5x squared plus 9x would give us exactly what we started with. So now it says, if that was 0, then we're right where we just said. I have 2 things that multiply together, and they could be 0. So tell me, one at a time, what could make them 0? So if I just looked at this part, if x equals 0 was going to be a true statement, what's x? Well, most people say x would have to be 0. Or the second one is, what if 5x plus 9 has to be the 0 part? That one's a little tougher to do in your head, but you still can do it. It's a simple 1-variable equation. So take your 9 to the other side and divide by 5. If you did that, you would have that one value of x that would make this 0. And it would make that second parenthesis 0. So if x was a negative 9/5, that second parenthesis would be 0. That would be a 0 of the function. So they're asking, what are our zeros of the function? Our zeros of the function are the 2 values that make both parts, so the first part and the second part, 0. So x equals 0, x equals negative 9/5. In order to do zeros of a equation, you have to factor first. So let's try, last but not least, q of x. Making these zeros first means you better factor. This looks like the chart method because I don't have an a term other than 1. So I'm going to say, what multiplies to give me a 108 that adds to give me 21? A lot of numbers here. Let's see. I like 12 and 9. I think we'll do it. And everything's addition, so if I say 12 and I say 9, 9 times 12, 18, carry the 1, 108, so we're good. And then 9 and 12 add up to give you 21. And so now again, back up here, if q of x is now 0, what makes me 0? So the brain says, what makes that parenthesis 0? Well, you can look at that one and say, well, if x was negative 12. Next parenthesis, what makes me 0? Well, again, you can look at that one and say, if x is negative 9. So your 2 zeros of your product in this case would be x equals negative 12 and x equals negative 9. Now those are going to be key pieces later on, but right now, zero product property, what makes me zero? All right, that's a lot to digest, and we will be spending several days on some factoring and give you several different sheets with factoring problems on. So bring any questions you might have, and I will also have a factoring sheet that I will bring to class for you.